Yeah. Then let me start. So first I will start with the problem which is there in the classical definition of the probability. So let me first restate the what is the classical definition of probability. So classical definition of probability. So it state that suppose that I have n possible outcomes, that means total sample size of my the number of outcomes of my in a experiment that can came is n, and out of it m of these outcomes are favorable to the happening of event A, then according to the classical definition of the probability, we say that probability of A is m by n. Now first of all, let's see what the classical how can we determine a probability of an experiment from the classical definition of the probability. So now the problem which I selected is, this is a problem from where we can clearly see that how can we use this classical definition to determine the probability. So first, if we roll two fair dice, and we want to calculate the probability that the sum of the outcomes is 7. Let me check this recording. So there is a number of possible ways by which we can calculate that what is the probability that the outcomes of the two the dice is 7. So first let me given way to calculate it. So first way, so you know that the a die in a die there are in the all faces there are 6 numbers are there. So one of the 6 number will be, if I roll a die, then one of these 6 number will come. 1 2 3 4 5 6. Now if we roll again another die, the same 6 number will come. So how many sums can be possible? So first of all, if two dice if in the two dice one comes, then that means in the both of the die, if the one comes, that means its sums will be 2. If in the one of the dice one comes and another in, okay, Okay, and one of the dice 2 comes, that means then 1 plus 2 is 3, so 3, the sum of the two dice can be 3. Similarly can be 4, 5, 6, 7, 8, 9, 10, 11 also possible. If one of the die, if the in the face of the one of the die is 5 and another is 6, then the sum of these two numbers is 5 plus 6 is 11, then 11 is also possible, and 12 is also possible. If both of the dies outcome is 6 6, then these 11 distinct sums can be possible: 1 2 3 4 5 6 7 8 9 10 11. Now out of these sums, how many so what is the how many times 7 occurs is 7, so that means the probability, then we can deduce from here the probability that the sum 7 is one of these 11 11 outcomes. So now here for calculating this this probability, I use the size of the sample space is 11, and what is the number that a favorable event A occur is 1, so that is 1 over 11. But this result is not right, this is wrong, so this is wrong. However, we calculate it using the classical definition, but we missed one point, that in the classical definition we have to use those outcomes which are equally likely, but we did not consider the outcomes which are not equally likely. Suppose these 6, how many ways the 6 can came? 2 4 4 2 3 3, so 3 ways, but 2 can only appear 1 1, so that means these 2 and these 6 are not equally likely. So according to classical definition, we have to consider only those outcomes which are equally possible. So there is another way you can calculate, but that is also again wrong. So let me first write that things, then I will say what is the right way. Let me introduce here what is the right way of calculating, right way of calculating this problem. Now which are the events which are equally likely? If I do a experiment, if I roll a die, then in single die the equally likely event is 1 2 3 4 5 6, but if we roll 2 die simultaneously, how many possible what are the possible? Okay, let me okay, then what are the possible events which are equally likely? That means one in one die, the face of one die can be 1 and another face die can be 1, so 1 1 is a possible event. Similarly 1 2, similarly 1 3. So in the similar manner, my now the outcomes which are equally likely will be 1 2 3 1 6, 1 2 3 4 5 6. Similarly 2 1 2 2 6. Similarly here 6 1 2 6 6. Now you can see that each of these outcome occur only one, and every outcomes possible outcome are equally likely. Now we can apply the classical definition of the probability, and we can calculate the probability. What is the probability of the sum? How many ways we can get how many ways we can get how many ways we can get 7? One of the possible ways is 3 4, right? 2 5 3 4 4 3 5 2 6 1 and 1 6. 1 2 3 4 5 6. Now that means now these 6 are my favorable outcomes to the event A, which is the sum of these two faces is 7. That means the what is the probability the sum will come 7 is 6 by out of how many 36. So that means 1 by 6. So this is the right probability. How I say this is right and that is wrong probability, because if we do the experiment, that means if we roll the actual die many times, we'll get the sum, the two faces of the sum will be closer to 1 by 6, not closer to 1 by 11. That's why these results are is wrong and that this result is right. So now we know that in the if we want to apply the classical definition, then we have to consider all the possible outcomes which are equally likely. So that is the main thing. Another thing is now I will given another problem which will in which we can clearly see what are the caveats in the definition of the classical definition of the probability. So one of the caveat is that in the classical definition, my sample size should be finite, right? And if it become infinite, if the sample size, that means if n becomes infinite, then we don't know how to use the classical definition to determine the probability. Now for then we have to represent the infinity by some number, and there can be possible ways to represent that infinity. Now to illustrate that things, I will give an example. So the example is the famous Bertrand paradox. Right. This paradox is if I want to calculate, so let me pose the problem. If I want to suppose that now the problem is we are given a circle of radius r and we wish to determine the probability P that the length of a randomly selected chord AB that the length of a randomly selected chord AB is greater than r by root 3. R by root 3 is r by root 3 is why I choose r by root 3, because r by root 3 is the length of the equilateral triangle which is inside, which you can draw inside the circle. So r by root 3 of the inscribed equilateral triangle. So let me check, is anyone is waiting here? Okay, so that is the problem. Now I will show you there are three possible ways or three possible solutions to the same problem, and all the solutions are different from one another. So these I will show you. The first, let me show you first way to calculate it. First way to using classical definition. First way to calculate the probability. So here I am my problem is, if I restate the problem is like problem. Let me first restate the problem here again. Problem is, if this, suppose this is a circle. This is not. Suppose this is a circle and suppose its radius is r, then our job is to find a chord AB whose length, suppose its length is L, this length would be greater than r root 3. So this is our problem. What is the probability that we can draw these, we can arbitrarily choose a chord, suppose AB, whose length is greater than r root 3. Let me solve first in first way. Okay. First way. So first way is, suppose this is a circle. No, my drawing is horrible. So this is a closest circle which I can draw. So this is a circle. Okay, now suppose there is another small circle inside. Suppose its radius is suppose r prime, and this is, I am drawing a tangent to this circle, to this point. Suppose this is AB, right, and this is r. Since this AB is a tangent to the smaller circle, suppose C, then this is a the angle will be 90 degree. This angle will be 90 degree, and this is r prime, this is r. So what is the distance between these 2 points? Suppose A and D. So from Pythagoras theorem we know that what is from Pythagoras theorem, what will be the distance between AD? Suppose this is suppose a length of AB is L, so this will be L by 2. So L by 2 square plus r prime square is equal to r square. So r prime square is r square minus L by 2 square. Now if you notice one thing, if I draw any chord which is in whose middle point is inside this circle, will be always, so let me first draw this clearly. So this is my problem of drawing. Okay, now if I draw any chord which is parallel to this line and whose middle point its middle point is inside this circle C, its length always larger than AB. That means that suppose A prime and B prime, its lengths always be greater than AB. Now if you draw any other chord, suppose in this direction, any other chords, you will get a parallel tangent to this, draw parallel tangent to this circle. You will get that any other chords which is inside the circle, and the length of that the chord which is inside the small circle C will be always higher than this tangent. So now we can apply, let me draw it here again clearly. So if I draw it again here, fine. So now if we draw a circle such that its tangent's length is L equal to r root 3, then I know that any chord which whose any point inside this smaller circle will be larger than this r root 3. So now we have to find the radius of this circle, and we know the chord length is r root 3 and this is r. So what will be the r prime square? Will be r square minus 3. If we put L equal to r root 3, so that means 3 r square by 4. That means r square by 4, which is r prime is r by 2. Now we know that the radius of the smaller circle is r prime is r by 2. Now if we represent that the measure of the how many line I can draw inside, this small circle by its area, that means then the number of favorable events, that means number of chord I can draw whose length is larger than r by root 3 should be proportional to this area of this circle. If I represent that is area of the circle, so that means it will be pi r by r by 2 its square. So it should be proportional to pi r square by 4. Now in the similar manner, how many chord I can draw inside this larger circle? So how many chords I can draw inside the larger circle, it should also be proportional to the area of this circle. So that is proportional to pi r square. So that means now from the classical definition, the probability that we can draw a chord whose length is larger than r root 3 should be pi r square by 4. This is the number of favorable events, and by the total sample size is total size of the sample space is pi r square. So that means it become 1/4. So so that means it becomes 1/4. So now we get the probability of getting a randomly selected chord whose length is L equal to r by root 3 is 1/4. So if we so if we measure the number of, if we measure the, since here you can see that here is the problem is the number of line you can draw here is infinite, so it is not finite number. So but if you want to represent that infinite things by any number, so if we represent that things in terms of area, we'll get the probability 1/4. But this is not the end of the problem. So now I will show you another method, another way to calculate the same probability, and you will see that with the some flow of logic, with the some flow of logic, the probability is different. So let me directly go to there. So now this is the second way, or this is the second solution of the same problem. So this is okay, let me, it is closest, let me draw it again. Right, that's the best I can do. Now here, now the same problem we will solve it in the slide different manner, and we'll get the different results. So that's the paradox. Now here, suppose if we choose a point A, this is the point B, point B, and now if I draw two line A, suppose B, suppose this is, suppose any name, suppose E and D. Now you see that the length of any chord, if I fixed, first of all, if I fixed A, and if I choose the any, okay, sorry, this point is not B, suppose this, name it, other thing F. Okay, now suppose that if I draw any chord, suppose this is AB. Now you see that the length of this AB chord is always larger than this AD. Always larger than this AD. Suppose this length is the length of the AD is, suppose the length of the AD is L prime and AB is L, then you will notice that the length L prime is always higher than the length L is always larger than the L prime. So that's it. So if I draw any chord which is B2, which one endpoint is A, and other thing is if it's inside this DE arc, then we know that the length of that chord will be automatically greater than the length of this chord will be automatically greater than of the AD or AE. Now let me find what is these what is the angle of this chord. Now if I draw, okay, no, so this is the length of this AF is, we know, 2R. Now since we know that any chord, now if we want to calculate the probability of drawing a chord whose length is larger than R by root 3, and we also know that any chord if we draw whose one point is A, another point is inside this arc, then it is automatically greater than A by D. So if we consider the length of the AE is R root 3, we can easily calculate the angle. So what is the angle? Sine theta, if we suppose is theta, then sine theta is equal to R root 3 by 2R, which is root 3 by 2. That means theta is equal to 60 degree. Now what is the total angle? From the symmetry we know that this total angle, this angle also be 60 degree, then total angle is 120 degree. So 2 theta is 120 degree. So that is the angle of that arc. If I draw AD, if I draw any chord whose end point is A and another point is between that between ADE, between this DE, then we know that that length of that chord will be automatically greater than L by R3. So here continuously. Now one can say that they are continuously joining and interacting. Okay, yes, so where was I? Yeah. Now one can say that this is wrong. Why it is wrong? Because one can say here I fixed one point A and changing another point B, so it is not the all favorable outcomes I count. No, my dear, it is true, it is you are right, but one thing we are missing here is that if I fixed A, it actually reduces the possible outcomes, but we also see the factor that when we reduce the possible number of outcomes of A, the possible numbers of B that satisfy this relation L whose length is greater than R by root 3 also reduce proportionally. So that way it does not affect to the probability. That's why we are safe here. Now that means now there is a one thing is left, that how many chord I can draw if I in this arc. Now what is if I now measure, that means if I now, since A is fixed, now so how many points I can draw in between D and E, that many line I can draw. So how many point I can draw in between, that can be represented by the length of this chord ED. And what its length? Its length is simply what is the angle? Okay, let me, it's simply okay, let me check it. It's simply 2 pi R by 3. Since how can I calculate it? Means this is the angle is 160 degree. So this what is the length of this arc is 2 pi r by 3. Now how many, if I fixed a, and how many line I can draw, how many chord I can draw, similarly how many point I choose on this whole circle, and the what is the periphery of this circle is, so if I represent the number of points which are in this periphery by its length. So what is the total length? It is the, that means the total, the sample size will be, if I fixed it, the sample size will be always 2 pi r, because the length of this two whole circles arc is 2 pi r. Now what is the probability then? Probability, if I use the classical definition, probability that if I arbitrarily choose a chord whose length is greater than r root 3 is actually number of favorable outcomes by total sample size is 1 by 3. Now you see that I calculate the probability in by using another logic. I will get the value of the probability is different from the what I calculate here, which is 1 by 4. Now it is coming 1 by 3. Now you see what is the paradox. Now the same problem I will get two right results. These results are not wrong, these results are actually right, but two different kind of solution. So, and I'll come to the third solution. Now third solution is, so this is the paradox, that same problem but I get three different solution while using classical definition. So now from the first way of calculating that probability, we know that this is r prime. If this is the length of this r by 2, then the length of this chord will be r root 3. That we already know. Now if you see here also, this is r by 2. Now suppose that you fix the direction of that chord, that now if you see if you draw any parallel line to this line, the length of that line will be automatically greater than r by root 3. So how many line you can draw, that is your favorable outcomes, right? And if you again say that here I fix the direction, now again that things is, it will not harm, it has no effect on that probability, because when I reduce the direction, it's also the total outcomes, that means it actually decreases the total number of outcomes and the favorable outcomes in proportionately. That's why that has no effect on the probability. Now if we measure what is the measure actually, how many line I can draw parallel to this line, is the length of this chord, the length of this r, then that many ways I can draw a chord whose length is root 3, and that is my favorable outcome. So r, that is the favorable outcome is r. Now how many line in general I can draw with keeping that constant that the parallel to this line or perpendicular to this to vertical line. So that will be also the length of this total chord, so which is nothing but 2r. That probability that length will be r root 3 is r over r by 2r, which is half. So that means again we get a probability which is different from the first two. So these the problem has only these three solution, and you see that these three solution are different. So the same problem, but we get three different right answer. So this is the problem. This is the paradox which is called Bertrand paradox. And then what is the problem here? The problem is only one thing, that is that we using classical definition of the probability to calculate it. And in the classical definition we use the only the finite classical definition is only will work only when the total sample size is finite. If it becomes infinite, then it will not work. And here one might also remark that the thing that three different solutions to the same problem. One might say that these three probability are okay. This is the paradox. So one might remark that these solutions corresponding to three different experiment. Why I'm saying that? If you see that here I use some constant, here also I use some particular constant, and here also I choose some particular constant. That's why one can say that these three are corresponding to three different experiments, and which is actually true, that these are the three results from three different experiments, but there is no way from the classical definition of probability to extract that information. That means the ambiguity is actually there in the main ambiguities are there with the classical definition of the probability. Classical definition of the probability. Okay, and what is the problem here? That problem is that the use in the definition, you see that we use the word favorable and equally likely. These words are problematic. So that's why we are getting since in the three cases the favorable things are different. In the three above example, the favorable things are different. So that's why we are getting three different kinds of probability. So that is the main ambiguities with the classical definition of the probability. So that's the things. Now I am going to another example which is related to the physical world. That is how we actually use how we will use the probability in our daily life, that we actually use it many times but we don't know. So that's we all know. I will emphasize that things again here. So if anyone asks the question, what is the meaning of the resistance of the resistor. Suppose that a resistor is commonly viewed as a two-terminal device whose voltage is proportional to the it is nothing to do with this classical definition, but I want to emphasize here the how we use actually the probability and uncertainty in our science. So that is, we always use the resistance R is the voltage V time by IT. Now if we, so this is a very simplified assumption we always use, but however this is a convenient way to represent the resistance. Actual resistance is a complex device with distributed inductance and capacitance having no clearly specified terminals that whose terminals also not specified. The relationship which I present here is only true with certain errors in certain frequency range and with a variety of other qualifications. Nevertheless, in the development of the theory of electricity, we want to use a simplified thing and a precise number to advance the theory. So that's why we use these definition. But while using definition, one should remember in his mind that this is only a observational thing and it is not a deterministic thing. Obviously it is a probabilistic thing, but we actually use it to development of the theory. So that's all I want to say, that here in the also calculating resistance we also use some sense of statistics and the probability to calculate the R, and the observation is nothing but the statistics. So that's all. Now I'll go towards the assignment sets that's were given previous in the previous course. So from here I will begin. I know many of you have already done this assignment, but I will again solve those assignment in this tutorial. So let me now from here I will solve some assignment problem. Okay, let's see some assignment problem. So these assignments are corresponding to the week 0 of the previous year's same course. So the first problem is, let A and B be two random events associated with a random experiment. Then consider the following statements. First statement: and if anyone has any doubt, then you can stop me at any point and ask me. P impossible event P impossible events equal to second probability A union A complement is 1. Third is probability of A 0, given that A is an impossible event. And fourth is P of sample space is 0. Now to solve this problem, let me restate the definition, that the axiomatic definition of the probability, which I will use to solve this problem. So first we restated the problem, the axioms of the definition of the axiomatic probability. So if the P is the probability of an event A, then the this probability is a real number, should be real number between this first axiom, that PA should be greater than or equal to 0. Second is that probability of whole sample space is 1. And third is probability of infinite many disjoint subsets, or disjoint subsets means in physical terms the probability of happening all independent events is 1 to infinity ei is the summation of I equal to infinity probability of happening that event. Okay, so first thing is P of impossible events. That means which is not P of impossible events if I consider all the events in the sigma in the omega, then what is the set of this what are the set that contains impossible events is actually phi. And we know from the corollary that has been taught in the lecture, that the probability of an event which belongs to the phi is 0. That means first statement is true, which means first statement is true. Now second, now what is the A complement? A complement is nothing but the sigma minus A. Sigma minus A means the A complement. Now that means if I draw a Venn diagram, this is A and the whole space is sigma, then means this is, if this is A, then all the other things which is not A is A complement. Now if we add these both A and A complement, we'll get what? That means the union of A and A complement, A and union of A and A complement should be this whole space. And from the second axiom of the probability, that P of sigma equal to 1, P of omega equal to 1, that means probability of A union A complement should be 1. So that means second statement is also true. Now the third statement, it's look like that it is true because A is an impossible event, so there is no probability of there is no probability that A will occur in future, since A is impossible event. So that means P of A is 0. But there is a subtle thing is here, that here these statements means P is 0 only when A is an impossible event. That statement is not true, that P of A is only 0 when A is an impossible event. Because if you of your example, that if I choose an interval between 0 to 1, and we know that to choose a particular point in between these this interval is actually 0, but that is not an impossible event, that is a possible event. You can choose a event, but the probability is 0. So if the statement means that the P of is 0 is if and only if A is an impossible event, that is false. So this statement 3 is not actually true. Another thing is the sample space probability of the sample space is not 0. I think it's 1. Let me see the problem again. Let me see the problem again. Yeah, it's 1. Volume, this is 1. Since from the axiom, from the second axiom, we know that this is true, so that means 1, 2 and 4 is true here. Right, now let go to this second problem. Now let's go to the second problem. Okay, okay, let me explain third a bit. Okay, third a bit. Okay, here the thing is that third means that the probability of that event A is 0. So that is true, that statement is true actually, that probability of an event is 0 if the A is an impossible event. That is true actually, because if that event is not, if there is no chance to occur that event, that means the probability of A is 0. So that statement is true, that if A is an impossible event, then the probability of A is 0. But it is not true that if probability, this is true, but it is not true that if probability of A is 0, this statement, that probability of an event is 0, is implies that the A is an impossible event. Okay, so the probability A will be 0 only if A is an impossible event. That is not true. The probability of 0 does not always implies that A is an impossible event. So that's why I have given I gave an example. Suppose that there is a suppose there is a interval between 0 to 1. So continuous interval. Let me there's a continuous interval between 0 to 1. Now if you choose any particular point, what is the probability that choose any particular point, since that the whole space, the length of the whole space is infinite, so to choose any particular point is actually 0, because there is a infinite numbers of points are there. So to choose a particular point is the probability of choosing a particular point is 0, but that is not an particular point. Suppose a particular point e1, suppose this is a particular e1 is 0, but this statement, the probability of choosing particular e1 is 0, does not implies that e1 will not happen any of the event. So e1 is not here impossible event, e1 is here a possible event. So that means p of e1 does not implies that e1 is an impossible event. So Ahmed, did you get it, or is it clear now? Okay, thank. Okay, now let's go towards the second problem. Suppose P is a set where element of the sets belongs to the natural number such that P is a prime number and which is less than equal to 5, and another set Q belongs to again natural number such that okay, P is a okay, Q is an odd number, Q is an odd number and less than 7, so less than equal to less than 7, okay, less than 7. Now we have to calculate, here n is the natural number, so then the number of proper subset, okay, this is the number proper subsets. So if element in a set, suppose that suppose there is a n element in a set, then the proper subset will, the total number of the proper subset will be 2 to the power n minus 1 if the n is the number of the element in the set. Now we have to calculate that what is that proper subset in proper subset, proper subsets of P intersection Q, right? Now first calculate what is the what is P is 2, 3, 5. These three are prime numbers and less than equal to 5. And what is Q? Q is again 1, 3 and 5. These three are odd numbers and less than 7. So what is the P Q intersection is actually 3, 5. So how many elements are there in P intersection Q? Only 2 elements. So what are the then what is the number of the proper subset of the P intersection Q? Will be 2 to the power 2 minus 1, that is actually 4 minus 1, that is actually 3. So that's it. Now another example is, okay, it's again from the set theory. So now let's move towards the new question. So now question number here 3, and the question is, suppose age is AB, which belongs to belongs to this, and A plus B is 4. So this is a set, and a set is B A B. This is a summation set, this is a product set, N and AB is 4. Now then what is the true statement here? It is a true statement. Statements are following. Okay, statements are following. Ace is a subset of P, to P is a subset or equivalent to Ace. 3, Ace is equal to P. 4th, Ace intersection P equal to 2, 2. So now let's see that. Now first, what is the Ace? Ace is Ace is how many numbers are there which if I add we'll get 4, excluding 0 because natural number, so excluding 0, so that means 1 3, 2 2, and again 3 1. This is the number of things. And product set is how many ways? 1 4, obviously 1 into 4 is 4, 2 into 2 is 4, and 4 into 1 is 4. So what is the intersection? SP is nothing but 2 2. So this is the right answer. This is the right answer. Okay, now let's move toward the next question. And since okay, okay, this is the thing. Okay, consider two sets A content A equal a set n belongs to this natural number which is less than 100 and divisible by 3, and B is n belongs to this such that n again less than equal to 100 and n is divisible by 5. Then the cardinality of set A union B. Okay, let's see that. So what is the cardinality? So first we have to use the following corollary. A union B is is equal to cardinality of A plus cardinality A plus cardinality of B minus cardinality of A intersection B. So what is the cardinality of A? Is the 100 by 3, because how many numbers are there? So 100 by 3, so which is less than or equal to 100. So how many numbers are there which belongs to A is 100 by 3 is actually and these symbols denotes the greatest. These symbols actually these symbols denotes the greatest integer. So 100 by 3, so you will 33 integer you will get, 33 natural number you will get which is less than 100. So this belongs to the set A, that is the cardinality. And what is the cardinality of B? So how many numbers you will get? So you will, in the set B there are 20 elements will be there, so that's the cardinality of B. Now what is the cardinality of A union B, A intersection B? That means the number which are divisible, which is obviously less than 100, and this intersection means that the both of that element will follow the both two property. Which property? One is divisible by 3, one is divisible by 5. That means in between 0 to 100 number, how many are there which are divisible both 3 and 5, both divisible by 3 and 5. So that means both divisible by 3 and 5 means both divisible by 3 into 5, 15. So that means how many numbers are there which are, now one interesting thing is there. So why 15? Okay, so you will see that the number, the smallest numbers between between 1 to 100 which is divisible by 15, divisible by both 3 and 5 is actually 15. So that means which number is divisible by 15 is actually both divisible by 3 and 5. So that means 100 by 5, how many numbers are there? So if you see, so it will be 6 numbers will be there. So we get the cardinality. So that means in the set of A intersection B only 6 element will be there. Now if I use this corollary, we'll get the A union B, the cardinality of A union B will be 33 plus 20 minus 6, which is actually 47. So that means cardinality is actually 47. Okay, yeah. Let's move towards a new question. Let's move towards a new question, that is question number 5. Here the question is, two fair dice are thrown simultaneously if the numbers x and y appear on the upper face the two dice, what is the probability that the number u is equal to 10x plus y is an even number. Okay, so the options are, let me give also the options also. A half, B 1/4, C 1/3, D 1/12. Who 1/12. Okay, yeah. So from the first, if you see from the first example, that applying classical probability, definition of the definition of the classical probability, how one can calculate the probability. We'll see that how many equally likely events are possible. We get that 36 equally likely events are possible. That means which are the total, what is the total size of the sample space, and all the distinctive events are equally likely. So what is the sample size is actually 6 cross 6, we know that 36. So 36 outcomes are possible, distinct outcomes are possible which are equally likely. Now we will apply the classical definition here. Okay, and it is an even number. So you already know that 10 into x is actually a, if you notice here, 10 into x, so is actually a even number. So even number, so we know that to get a even number we have to add two even number. If we add with the even number with the odd number, so let me, even plus even number will get even number. If we add odd plus odd number, we will actually get even number. If we add even number plus odd number, we will get odd number, and similarly odd number plus even number is odd number. So here already know 10x, since 10 is even, 10 is even since 2 multiplied by 2, so that means 10 is also an even number. So that means we have to know what is the probability that y will be a even number. So that's it. If we know what is the probability of that y is a even number, so then we actually know what is the favorable number of equally likely outcomes which is in favor to this event A. Then we can actually calculate the probability. Now you see how many even numbers are there in 6. So it's actually 2, 4 and 6, only 3. Now we know that which are the equally likely events here. Which here equally likely events are like this, that in first die 1 comes, in second die suppose y comes. Y don't know. So, and we know that how many ways these in my equally likely events I will get to in the second die 2, because I need in the second die an even number, y is even, so y should be between 2, 4 or 6. So how many ways I will get to, that can be 1, 2, maybe 1, 2, okay, that can be 2, 2, 3, 2, 4, 2, 5, 2. In the first die 1 comes, in the second die 2 comes, first die 2 comes, 2 comes, similarly the 6, 2. How many are there? Let's count. 1, 2, 3, 4, 5, 6. So 6. And similarly in place of 2, if we use 4, or another 6 will get another 6. Similarly 1, 4, 2, 6, 4, like this. So 6, and if we use 6 again similarly 1 6 2 6 3 6 4 6 5 6 6 6 will come. So that means total 18 outcomes will be in the favor of that u is an even number. So my favorable outcomes, the number of favorable outcomes, that means m is 18, and what is the total size of the sample space which are equally likely is 36. So what is the probability that the pu is an even number is actually 18 by 36 is actually half. So that means first answer first is correct. This answer is correct. Let me move towards the next question, which is next question. Okay, question number 6. So let E and F be two events with P E union F is equal to 0.6, P of E, probability of E is 0.3, probability of F is 0.4, then probability of E intersection F complement plus probability of E complement intersection F, what will be that? Okay, let's do it. Okay, I will show you how to calculate these things with Venn by using Venn diagram, right? Okay, let's see. So there is a event E, there is a set of event F, so this is E. Let me write E inside. This is E, this is F, and there is an intersection. Intersection means they are not disjoint, they are not independent events, they are dependent events. So there is a intersection. So intersection value is suppose there is an intersection because P union is not 0.4 plus 0.3, 0.7, it's 0.6. One other thing I want to mention here, that the union, if these two are disjoint set, that means two events are independent, then the P union F's will be 0.3, only 0.3 plus 0.4, only the addition of this. Since it is 0.6, that means there is a some connection between the PU and F, so we double count it here, so we have to subtract that from it. So here you will see that this is 0.6, that means P, okay, union, okay, right, let me write it properly. P union E plus P union F minus P E intersection F. What is the value of P E intersection F? Will be PE plus PF minus P E union F plus 0.4 minus 0.6, which is 0.1. So that means there is some intersection, and intersection value is 0.1. Let me use the Venn diagram to what is the what that E intersection F complement will look like. So suppose, let me draw it here properly, then it will be easier to follow. So suppose this is E, this is F, this is E, this is F. Now I want E intersection F complement. What is it? E intersection F complement. What is the F complement? F complement is the outside. Suppose this is my whole space. Suppose this is my whole space. Whole space means omega. This is my whole sub omega. So F complement means that the outside regions, this region, outside region of F in the sample space. That means all include those things. Only it's exclude the F. So that is F. That is F complement, right? That is F complement. Now we want to know what is the intersection between F complement and E. Now we will see that what is the intersection, that means what is common area between FC and E, and you will see the common area is only this part, only this part is only common. This part is actually E intersection FC. Okay, and what we know, that means if we subtract E from this region, we'll get E intersection FC. What is this region? This region is nothing but E intersection F. So that means if we subtract E intersection F from E, what we will get? We will get E intersection F complement is nothing but E minus E complement F. Okay. Now we know the probability of E complement F C is equal to probability of E minus E intersection F. And from the corollary we know that the probability of these two things is probability of E minus okay, probability E minus probability of E intersection F. What is the probability of E? Probability E is 0.3. Okay, 0.3. And what is the probability of E intersection F? That is that we calculated. It is 0.1. So 0.1, that means it is 0.2, right? It is 0.2. And similarly, what is the probability? What is that? That means what is the E intersection F complement? In the similar manner, what is it is nothing but F minus E intersection F. What is the probability? E intersection FC. And from the corollary that you have already learned from your previous class, that this is the probability of F minus E intersection F is nothing but P of F minus P of E intersection F. What is the value of PF? Let me check. What is the value of PF? PF is 0.4. So 0.4 minus this is 0.1, that means 0.3. So what is the value of P in F intersection E complement? Yeah, Ahmed raise a point that when we calculate when we calculate that E intersection FC, right? E intersection FC, he said that it should be F minus F intersection E. Oh, what? Yeah. Okay. it should be yeah, Ahmad is right that he said that it should be F intersection E complement. What I write? Okay, here, right? It should be F intersection E complement. Thank you, Ahmed. So it should be F intersection E complement. F intersection E complement. So that is point 3. Now what is the question? Question is what is the if I add these two number, what is that? So probability of E complement F plus probability F complement EC is actually 0.2 plus 0.3, which is actually 0.5. So that is the answer. Now let me move towards the next question. Okay, what is the next question? Next question is A and B. Okay, let me write it. Let A and B be two events such that P of A is equal to P of B is equal to 1, then the value of PA intersection B. Okay. Probability of A and probability of B is 1. So there are many different ways to solve this question. So let me. So first, if A and B is equal to 1, since we know that the probability from the corollary, you can actually show that probability of A should be less than equal to probability of A union B. If there are two events A and B, then probabilities of A or probability B or probability A, the both actually the value of these two probabilities both should be less than equal to the union of these two events. That means since we know that this is 1 or less than equal to P of A union P, and from the statement, if you remember, if you recall that what is the classical definition, what is the axiomatic definition, let me bring it here. What is the axiomatic from the from what is the axiomatic difference? Here it is. From the axiomatic axiomatic definition of the probability, the first statement, first axiom, that is the probability of any event should be greater than 0, and okay, that's the problem. Okay, it's not going. What the problem? I don't know. Sorry guys, I think some glitch. Okay, it automatically. So probability of less than equal, so that means, and the probability of any event cannot be larger than 1, larger than, so the probability of any event, probability from the corollary we know that probability of any event should be less than equal to 1. So that means since we want to calculate the probability of A union B, it should also be less than equal to 1. That means the probability actually greater than equal to 1 and less than equal to both. That means this number should be equal to 1. That means probability of A union B should be 1. There is nothing other possibilities. That means if we know, we already know what is the formula of that P A union B is P A plus P B. Sorry. P P minus P A intersection B. That means P A intersection B is P A intersection B is P A union P minus oppositely P A plus PB minus P A union P. If I put the value 1 plus 1 minus 1, which is 1. So this is the thing, another thing to that means the value of the A intersection B is equal to 1. Now another way to see the same problem. Now since that axiomatic definition of the probability is actually there is no ambiguity, you will see that if I calculate it in another way, you will also get same result. So for suppose that is, we know that probability of this is 1, so that means A contains all the events, is A contains all the events of the experiment. That means A itself sigma, and also B also contains all the events, so B also sigma. That means the A, since sigma contains all the events, B contains all the events, that means A or B in some sense of same. So A or B are not different from each other. So if A and B are not different from each other, so this should be equal A or B. From the Venn diagram you also can see, suppose that this is A, this is A, and the same thing is B also. What is the intersection? Intersection is A or a B. So what is the probability of A intersection B? That will be PA or PB, which is 1. So this is the thing. Now this is the another thing. Now let's move toward the our next question. Okay, next question. Yes, next question is question number 8, I think. Consider all families with 2 children where the probability of each child being a boy or a girl is 1.5. Now one randomly selected selected family has one child as boy. What is the probability what is the probability that the other child is also a boy? So that is our problem. Let me use blue. Now this thing, at the first glance I also make the mistake that since there is a two child and every child has let me first give that okay, there is a no okay. At first glance I have also mistakenly thought that the probability should be half, because you see that there are two child, and since in the first statement, if you read it correctly, all families with two children, where the probability of each child being a boy or a girl is half, right? So each child being a boy or being a girl is half. So if it doesn't matter, since the probability of one I have thought that probability of single children is boy or girl is same whatever the other children is, that means the probability should be half. So the probability if a children is boy, then the other children is also be boy is half. There is no other thing. But I forgot that classical definition. This is, I will solve this through a classical definition, that I have to consider. I have also mistake that same thing, that I haven't considered the equally likely events. I thought that sample size is since the one child is boy, the other child can be boy and girl, right? And what is the probability of boy and girl? Half and half. So I have mistakenly thought that the equally likely event is B and G. So these mistake can anyone can do. So let me show you from the classical definition how you actually solve this question. So let first see the what are the possible outcomes which are equally likely. We'll start from there. So equally likely events are, suppose both children are boys, one boy, one girl, one boy, and both of them are girls. These could be possible equally likely events, right? These equally likely events. Now since the probability, now what I have to calculate, the what is the probability. First state for writing purpose, let me write two statement. E means E represent the statement one child is boy, and F is the second child is boy, right? So we know that one thing we know, what is the probability that one child is boy and the second child is boy, then both child are boy, right? What is the probability that E intersection F, that means E intersection F means the both of these two statements are true. That means first child is boy and the second child is also boy. Right, the first child is so that is one of these four event 1 2, so that is 1/4. Now another thing, what is the probability that one child is boy? So that is 3/4. So you can see that here the one child is boy. So that is the probability. Now from there is a, I don't know you know or not, but there is a in probability there is a theorem called Bayesian theorem, from Bayesian probability theorem. So from Bayesian theorem, applying Bayesian theorem, we can calculate the conditional probability. I think since this is the assignment corresponding to the week 0, I think you don't in the class the conditional probability has not been introduced yet. So let me tell you that there is a probability that here I have to calculate the conditional probability, that what is the probability that second child, if is the second child is a boy, given that one child is a boy, first child is a boy, sorry, one child, the first child has one child as a boy. What is the probability that other child, okay, sorry, and not it is second child, this I think mistakenly right is not second child, this is other child, right? So what is the probability that other child is a boy given that one of them is boy? This is the sign of writing conditional probability. I think in the next couple of lectures in the course you will be introduced to this conditional probability. So that this is the conditional probability, and according to the Bayes theorem, this conditional probability will be equal to the P intersection F by P of E. That P of intersection F means, if I say it in words, that means what is the probability that that event E has been occurred, that event E has been occurred already, and in the future the F will occur. So if you see that, that means you will see that if I write it here, that means you know that P or E already occurs, and out of the E, since I have to calculate that the E had already occurred, what is the probability that now in the next round F will occur, or next round, or in terms of this example, that you already know that one child is a boy, what is the probability of that other child also boy? You know that things. So you know that things, that means what is the probability? You have to calculate. So that is first what I am saying, that what is the total probability, total number of event where the one child is boy. So that out of that set means, if suppose that if we say it Bayes theorem, if I want to say that Bayes theorem in terms of words, so that's why I'm explaining it. So suppose that is E, there is a set. So suppose, let me write it properly. Suppose that E has occurred, so E is a set. Now out of E, since I know E already occurred, so out of E, how many F will occur? So how many F occur? So I know that if it is F, so since I already know in the sample space this part is actually true, that part has not been occurred, so this part already true. So out of E, how many F will occur? So only this intersection part, right? So now if we want, so probability of E is a measure of something. So in terms of words, you will visualize now that the probability that E has already occurred. What is the probability F will be occurred in the F will occur? It is the probability of E intersection F and to probability of E. So that is the thing here, and it is nothing but P intersection is 1/4, and that is 3 by 4 is 1 3. Without introducing this conditional probability, you can also calculate by from the classical definition. Let me show that thing, that will be easier for you. So let me first show you that I know what is my sample space. What is my sample space is BB, which are equivalent BB, BG, GB and GG. Now out of them how many events contain that that one of the child is a boy. You can count 1 2 3, only 3 of them, only 3 of them has only one boy, and out of them in which event both of them boy is 1, so favorable outcome is 1. So that means the probability of the both children are boys is 1/3. So that way you can calculate this type of you can calculate the probability of this type of problem. And always remember that when you have already given that something has happened or something has occurred, that means you have to calculate the conditional probability. So conditional probability, otherwise you will also mistake that I have did previously, that I thought that I haven't considered that it is a problem of conditional probability, and I think that the probability of the next probability of other children being boy or girl is half, but that is not true. Here I have to calculate the conditional probability, that's all. So that is the 8. Now let me go towards the question number okay, question number 9. Question number 9 is okay, question number 9. Let me quickly state the question. A box contain 7 non-defective bulbs and 3 defective bulbs. 2 bulbs are selected randomly from the box. Two boxer, okay, who is admit at the last moment someone wants to join in this tutorial. The probability that at least one bulb is defective. What is the probability? That the probability at least one bulb defective is, what is the probability? So let's calculate that. Now what information has been given in this problem, that 7 bulbs are there which are non-defective, and 3 bulbs are there defective. So there are total 10 bulbs. So how many ways you can take 2 bulbs from 10 bulbs? If suppose that the with consideration that the 10 bulbs are distinctive, that you can you actually know that which bulb is which. Means suppose that in the every bulb there is a every bulb there is a number 1, similarly 2, 3. Yeah, and yeah, after saying you know that this bulb is number 2 bulb, this bulb is number 3 bulb. So now how many ways you can choose 2 bulbs out of them? So that is 10C2, which is actually, you can see this is a thing. Okay, this is 10C2 ways. Now 10C2 ways you can choose the bulb. So that is a number 10 factorial by 10 minus 2 factorial into 2 factorial, and this is 10 factorial by 8 factorial 2 factorial. I suppose you all knows this factorial and the combination thing, right? And 10 into 9 by 2, 45 ways. Now in 45 ways you can choose 2 bulbs. Now quickly I will give you if someone does not know how I get this formula for them, I want to emphasize how I actually get this. Suppose that I have a smaller number of bulbs. Suppose that this is example. How I get this number. It is nothing to do with the problem. I will get back to the problem, but first give an example. So how many ways? Suppose that you have something that, suppose 1, 2, 3, 4. Suppose that you have 4 numbers and you have to randomly choose between these 4 numbers. How many ways you can choose it? So first you can choose any one number of 1, 2, 3, 4 between. So 1, 2, 3, 4. That means you can choose. Let me write it. First you can choose 1 can choose 2, 1 can choose 3, 1 can choose 4, right? Now another one can also choose 1. Now another one can also choose here. Another one also is 1. This is 2, 2, 3, 2, 4, 2, right? So that means if you see that here, or suppose write it A2 and suppose, okay. Now here I okay, let me write it. So that means here another thing is 1, 3, 2, 3, 3, 3, 4, 3, and 4, 1. Actually 1, 4, 1, 4, 2, 4, 4, 4, and 3, 4, and 4, 4. Now you see that with bulb, if you already choose one bulb, suppose you choose already one, you have to simultaneously choose 2 bulb. That means if you already choose bulb number 1, you cannot second bulb cannot be bulb number 1. So that means this 1 cannot be possible, 2 cannot be possible, 3 cannot be possible, 4 cannot be possible. So that means how many ways you can choose? 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and how many? There's 3 here, 3 here, 3 here, 3 here. That means 4 into 3. Now you can see the pattern. When you simultaneously choose 2 bulbs, then means in the first bulb you can choose 1 to 10, between 1 to 10 in here. For 10C2 case, if I get back to here, 10C2 case, you can choose first bulb between 1 to 10 any number. So that means in 10 ways you can choose one bulb. And how many are left there? 9 bulbs. And how many bulb and how many ways you can choose bulb? 9 ways, because 9 more bulbs you can choose there. So 10 into 9. So that way you get 90 number. Now you will see that this 2, 1 and 1, 2 will make no difference, because you choose first bulb number 1, second bulb number 2, it makes no difference. That means I have to divide by 2, because this is symmetric. 1, 2 and 2, 1, 1, 2 and 2, 1 came. Similarly 3, 1 and 1, 3 came. So I have to divide. So that's the way you get 45. So that's the all I want to say. Okay, in the last moment someone wants to join. Very crazy person he is, maybe, I don't know. So 45. So that is the 45 ways you can choose 2 bulbs out of the 10. Now I have to calculate the what is the probability that at least one bulb is defective, right? So I have to calculate what is the one bulb is defective. So if I choose that both suppose an event E is that both bulbs are okay, both bulbs are non-defective. If both bulbs are non-defective, if I get this set that where the both bulbs are non-defective, what is the complement of it? So at least one bulbs are defective. If two, here is represent the set that both bulbs are defective. What is complement? Its complement will mean at least one bulb may be defective or two bulb can be defective. So if we can calculate the what is the probability the both bulb can defective, then we know that E complement means a 1 minus E, and we get that at least one bulb is defective. So what is the probability? 1 minus that how many ways we can choose non-defective bulb. So I have to calculate that what is the probability of choosing a non-defective both bulb non-defective. So how many ways I can choose non-defective bulb? So sevens are there, and out of 2 I have to choose. So 7C2, similarly in 7C2 ways I can choose. So probability E should be 7C2 in 10C2. If we calculate it, you will get it is nothing but 21 by 45. Here again 21, again from here also from the previous formula you can also get from the 7 how many how many ways I can get pick 2 bulbs. It should be 7 into 6 by 2, so which is 21. Basically that is that. So 21 by 45. So what is the probability that at least one of them are defective? Is nothing but 1 minus no bulb is defective, which is 1 minus 21 by 45, which is 45 minus 21 by 45, so it is basically 24 maybe by 45, and that is 8 by 15. So that is 8 by 15 basically. So that's it. The result is 8 by 15. So I think that's all for the today's tutorial, and I will again see you guys at next Saturday. So thank you for joining. If you have any questions, you can ask me, or otherwise you can leave. I will wait for next 2-3 minutes, then I will also leave. If you guys have any question, you can ask me, or you can leave.